A single-phase transformer is basically two coils of insulated copper wire, called windings, wrapped around a magnetic core. The core is made of thin sheets of iron called laminations stacked together. The laminations keep the core from heating up because they limit circulating eddy currents. Core types. Shell type, the windings are placed on the outside of the core, and the core surrounds them like a shell protecting a turtle. Core or EI type. The windings sit in a central limb, and two E-shaped pieces are placed on either side, forming a closed magnetic circuit similar to a book spine. Toroidal core. The core is a donut-shaped ring. Windings are wrapped uniformly around it. Because the magnetic flux stays inside the ring, stray fields are minimal, and efficiency is high. Construction steps. A. Cut laminated steel into the chosen shape. B. Stack the laminations and bolt them together. C. Insulate the primary winding and place it on the core. D. Add the secondary winding. E. Secure everything with varnish or resin and attach terminals. The whole assembly is mounted in a protective metal or plastic enclosure. When an alternating voltage is applied to the primary winding, an alternating magnetic flux phi of T is created in the core. According to Faraday's law, a changing flux induces an electromotive force, EMF, in any coil that links that flux. This is called mutual induction. For a coil with N turns, E equals negative ND phi over dt. If the primary has N1 turns and the secondary N2 turns, the induced voltages are V1 equals negative N1 d phi over dt, V2 equals negative N2 d phi over dt. Because the same d phi over dt appears in both equations, their ratio depends only on the turn numbers. V1 over V2 equals N1 over N2. This is the turns ratio formula. It shows that if the secondary has twice as many turns as the primary, the secondary voltage will be half of the primary, step down, and vice versa for a step-up transformer. The negative sign indicates a 180-degree phase shift. The induced voltage opposes the cause, but in magnitude calculations we ignore it and use absolute values. Explanation: the turns ratio relationship directly gives us voltage, current, and apparent power relations. For an ideal transformer, no losses. Voltage ratio: V sub 1 over V sub 2 equals N sub 1 over N sub 2. Current ratio: since power P equals V, I must be equal on both sides. V sub 1 I sub 1 equals V sub 2 I sub 2. We get I sub 1 over I sub 2 equals N sub 2 over N sub 1. Power P sub N equals P sub out, ideal case. Sample calculation. Suppose a transformer has N sub 1 equals 200 turns primary and N sub 2 equals 50 turns secondary. It is connected to a 230-volt AC source. Voltage on secondary: V sub 2 equals V sub 1 times N sub 2 over N sub 1 equals 230 volts times 50 over 200 equals 57.5 volts. If the load draws 5 amps from the secondary, the primary current is I sub 1 equals I sub 2 times N sub 2 over N sub 1 equals 5 amps times 50 over 200 equals 1.25 amps. Apparent power on each side: P equals V sub 1 I sub 1 equals 230 times 1.25 equals 287.5 volt amps, and V sub 2 I sub 2 equals 57.5 times 5 equals 287.5 volt amps. The numbers match, confirming the relationship. These simple equations let engineers design transformers for any required voltage or current level simply by choosing the appropriate turn ratio. Real transformers are not ideal. Two main loss mechanisms exist. Core iron losses caused by hysteresis, energy spent to magnetize-demagnetize the core each cycle, and eddy currents, circulating currents induced in the laminated steel. They appear as a constant power draw, independent of load, usually a few watts to a few hundred watts. Copper I squared R losses, resistive heating in the windings, proportional to the square of the current. P sub Q equals I sub 1 squared R sub 1 plus I sub 2 squared R sub 2. Efficiency eta is the ratio of output power to input power. Eta equals P out divided by P in equals P out divided by the sum of P out, P core and P Q times 100%. Regulation indicates how much the secondary voltage drops when a load is applied. Percent regulation equals the difference of V no load minus V full load divided by V full load times 100%. Numerical example. A 1 kilovolt ampere, 230 volt over 115 volt transformer has core loss equals 5 watts constant. Primary resistance R sub 1 equals 0.5 ohms. Secondary resistance R sub 2 equals 0.2 ohms. Full load secondary current I sub 2 equals 1000 volt amps divided by 115 volts equals 8.70 amperes. Primary current at full load I sub 1 equals 115 divided by 230 times I sub 2 equals 4.35 amperes. Copper loss, P sub Q equals I sub 1 squared R sub 1 plus I sub 2 squared R sub 2 equals 4.35 squared times 0.5 plus 8.70 squared times 0.2 approximately 9.45 plus 15.15 equals 24.6 watts. Total loss equals 5 plus 24.6 equals 29.6 watts. Efficiency, eta equals 1000 divided by the sum of 1000 and 29.6 times 100 approximately 96.1%. If the no-load secondary voltage is 115 volts and the voltage under full load falls to 112 volts, regulation equals the difference of 115 minus 112 divided by 112 times 100 approximately 2.68%. These numbers illustrate why designers strive for low-resistance windings and high-quality core material. Explanation: the equivalent circuit of a single-phase transformer replaces the magnetic coupling with ideal and non-ideal elements that behave electrically. The most common model referred to the primary side contains RC core loss resistance parallel to the magnetizing branch, XM magnetizing reactance also parallel, Rec equivalent resistance representing copper loss referred to the primary equals R1 plus the square of the turns ratio times R2. Xec equivalent leakage reactance equals X1 plus the square of the turns ratio times X2. The source voltage V1 is applied, and the secondary voltage appears across the reflected load. Impedance computation example. Given primary resistance R1 equals 0.4 ohms, leakage reactance X1 equals 1.2 ohms. Secondary resistance R2 equals 0.1 ohms. Leakage reactance X2 equals 0.3 ohms. Turns ratio equals 2. Reflected secondary values to the primary side. R'2 equals a squared times R2 equals 2 squared times 0.1 equals 0.4 ohms. X'2 equals a squared times X2 equals 4 times 0.3 equals 1.2 ohms. Total equivalent resistance Rec equals R1 plus R'2 equals 0.4 plus 0.4 equals 0.8 ohms. Total equivalent reactance Xec equals X1 plus X'2 equals 1.2 plus 1.2 equals 2.4 ohms. Thus, the series impedance seen from the primary is Zec equals 0.8 plus J 2.4 ohms. The magnitude Zec equals the square root of 0.8 squared plus 2.4 squared approximately equals 2.55 ohms. This impedance determines voltage drop and short circuit current during tests. No load open circuit test. Connect the rated voltage to the primary and leave the secondary open. Measure primary voltage V sub awk, current I sub awk, and input power P sub awk. Because the secondary is open, the current is only the magnetizing current small lagging. From measurements we obtain R sub C equals V sub awk squared divided by P sub awk. X sub M equals the square root of open bracket V sub awk divided by I sub awk close bracket squared minus R sub C squared. Worked problem. A 500 volt ampere transformer is tested at 230 volts. The no-load current is 0.2 amperes, and the input power is 30 watts. R sub C equals 230 squared divided by 30 approximately 1763 ohms. Z sub awk equals V sub awk divided by I sub awk equals 230 divided by 0.2 equals 1150 ohms. X sub m equals the square root of 1150 squared minus 1763 squared. Note that R sub C greater than Z sub awk. The calculation shows that magnetizing current is dominantly reactive. Proper rounding gives X sub m approximately 830 ohms. Short circuit full load test. Short the secondary terminals, apply a reduced voltage to the primary, usually 5 to 10% of rated to allow rated current to flow. Measure primary voltage V sub SC, current I sub SC, and input power P sub SC. The core losses are negligible because flux is tiny, so the measured power is copper loss. Parameters: R sub EC equals P sub SC divided by I sub SC squared. Z sub EC equals V sub SC divided by I sub SC. X sub EC equals the square root of Z sub X squared minus R sub X squared. Worked problem. For the same transformer, the short circuit test gives V sub SC equals 15 volts, I sub SC equals 2.17 amperes rated current, and P sub SC equals 8 watts. R sub EC equals 8 divided by open bracket 2.17 squared close bracket, approximately 1.7 ohms. Z sub EC equals 15 divided by 2.17, approximately 6.91 ohms. X sub EC equals the square root of 6.91 squared minus 1.70 squared, approximately 6.70 ohms. These values match the equivalent circuit numbers derived earlier, confirming the model. Explanation: the magnetic flux in the core depends on the supply frequency F and the applied voltage, from Faraday's law for a sinusoidal source. V equals 4.44 times F times N times phi max. Rearranged, the maximum flux density B max equals phi max divided by A, where A is core cross-section, becomes B max equals V divided by open parenthesis 4.44 times F times N times a close parenthesis. If B max exceeds the material's saturation flux density B sat, typically 1.2 to 1.5 Tesla for silicon steel, the core can no longer carry additional flux, causing a sharp rise in magnetizing current and overheating. Design example. Design a 230 volt to 12 volt step-down transformer for 60 Hz operation using a steel core with B sat equals 1.4 Tesla and core area A equals 4 square centimeters. That is 4 times 10 to the minus 4 square meters. 1. Choose a primary turn count that keeps B max safely below saturation, say 90% of B sat. B design equals 0.9 times 1.4 equals 1.26 Tesla. 2. Solve for N1. N1 equals V1 divided by open parenthesis 4.44 times F times A times B design close parenthesis equals 230 divided by open parenthesis 4.44 times 60 times 4 times 10 to the minus 4 times 1.26 close parenthesis, approximately 1,720 turns. 3. Turns ratio required for 12 volt secondary. A equals N1 divided by N2 equals V1 divided by V2 equals 230 divided by 12, approximately 19.17. Hence N2 equals N1 divided by approximately 1,720 divided by 19.17, approximately 90 turns. The designer may round the counts to the nearest whole number, for example 1,788, and verify that the resulting B max stays below the limit. If the frequency were increased to 50 Hz, as in some regions, the same voltage would produce a higher flux, so more turns would be needed or a larger core area must be chosen to avoid saturation. Explanation: below are 3 typical exam-style questions that test understanding of the working principle of a single-phase transformer, followed by concise solutions. Question 1. A transformer has 500 turns on the primary and 100 turns on the secondary. The primary is connected to 240 volts RMS. Part A. Find the secondary voltage RMS. Part B. If the secondary supplies a 10 ohm resistive load, calculate the primary current. Part A. Turns ratio A equals N1 over N2 equals 500 divided by 100 equals 5. Voltage ratio V2 equals V1 divided by A equals 240 divided by 5 equals 48 volts RMS. Part B, load current on secondary I2 equals V2 divided by R equals 48 divided by 10 equals 4.8 amperes. Primary current I1 equals I2 divided by A equals 4.8 divided by 5 equals 0.96 amperes. Apparent powers. Input power P in equals 240 times 0.96 equals 230.4 volt amperes. Output power P out equals 48 times 4.8 equals 230.4 volt amperes. Ideal. Question 2. During a short circuit test, a 1 kilovolt ampere transformer shows a primary voltage of 12 volts, current of 10 amperes, and input power of 7 watts. Determine the equivalent resistance and leakage reactance referred to the primary. Equivalent resistance, Rec equals short circuit power divided by short circuit current squared equals 7 divided by 10 squared equals 0.07 ohms. Equivalent impedance, Zec equals short circuit voltage divided by short circuit current equals 12 divided by 10 equals 1.2 ohms. Leakage reactance, Xec equals the square root of Zx squared minus Rx squared equals the square root of 1.2 squared minus 0.07 squared, approximately 1.198 ohms. Question 3. A 60 Hz transformer is required to deliver 120 volts at the secondary with a maximum flux density of 1.2 Tesla. The core cross-section area is 3 square centimeters. Compute the minimum number of primary turns. Convert area, A equals 3 times 10 to the minus 4 square meters. Use N1 equals V1 divided by 4.44 times F times A times B max. Assuming a standard 230 volt supply, N1 equals 230 divided by 4.44 times 60 times 3 times 10 to the minus 4 times 1.2, approximately 2030 turns. If the supply is 120 volts, that is, the transformer is used as a step-up. Replace 230 with 120, giving N1 approximately 1060 turns. These problems reinforce the core ideas. Turns ratio controls voltage, current follows the inverse ratio, and test data allow extraction of equivalent circuit parameters.